are conceptualized as points, so the basic fundamental contact of area and pressure is neglected. That we attack using our sensing system, which is available in IIT Madras.
If you feel you have a strong passion to pursue research in engineering, technology and science, and yours is the quest for innovative solutions, IIT Madras is the place to be.
The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
There should be somebody who is sort of a caring student who reaches out to every one of those students. That's how Mithra was born. Given that a student at the age of 17 joins us and matures to be an adult at the age
Hello and good day to everyone. Thank you for joining us today. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 50th webinar from the IRIS webinar series. My name is Richard George Philip, and I'm a part of the Office of Global Engagement. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research facilities in India. IIT Madras is proud to have been selected as one of the Institute of Eminence. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway at IIT Madras. As a part of these initiatives, the IRIS webinar series aims to showcase the innovative research being generated to various stakeholders like the students, researchers, industrialists, and policymakers. From the Microscopy technology cluster, the research initiative presenting today is titled Advanced Microscopy and Materials, led by Dr. S. Sankaran. Materials form the basis for most of the technology advancements in every sphere of life. The focus of this proposed center is to understand the scientific origin of the properties down to the atomic scale through the advanced microscopy and modeling tools. Professor Sankaran is a faculty at the Department of Metallurgical and Materials Engineering at IIT Madras since 2007 and currently is engaged in the research field of microstructure mechanical behavior correlations and electron microscopy. He is also professor in charge of Central Electron Microscopy Facility at IIT Madras. Thank you for being with us today, Professor Sankaran. It is my pleasure to introduce the moderator for the webinar today, Professor Gerard Wilde. Professor Gerard Wilde is a director of Institute of Materials Physics at University of Münster, Germany. He is also a scientific member of Center for Nanotechnology at Münster. Presently, he is serving as a chairman of the Materials and Metal Physics Division of German Physical Society. Thank you for being with us today, Professor Gerard. We are very excited that you could be a part of this session.
Thank you, my pleasure.
We also have a very distinguished panel with faculty from across various departments at IIT Madras joining us. We have professors Dr. Sudhakar Chandran, Dr. Subramanya Sharma, Dr. B.S. Murthy, Dr. Satyesh Yadav, Dr. Somnath Bhattacharya, Dr. Srikant Vedantam, and Dr. K.C. Harikumar with us today. A very warm welcome to all of you. And before we start, a note to the participants, please use the Q&A to enter your questions and upvote questions that interest you so that the moderator can prioritize them later. Over to you, Professor Sankaran.
Thank you, Richu, for the nice introduction. I will share my screen now. Is it visible?
Yeah.
Good evening to all of you, and welcome to this IRIS webinar series on microscopy. And I would like to thank our director, Sir Bhaskar Ramurthy, for giving us an opportunity to engage our colleagues to this type of research. So what you see in this slide is advanced materials, which is primarily related to energy and transport. You all agree with me, from the Stone Age to silicon chip, materials are the building blocks of any society and civilization. And the materials which are exhibited in these slides basically are, the investigators who are working on currently proposes this center. The materials ranging from the nanomaterials, like quantum dots, 2D materials, and lithium-ion batteries, which are all part of this, futuristic energy materials. And the investigators also working on the advanced high-strength alloys, for example, the third generation high-strength steels, and you take the nickel-based superalloys, which are the functioning operating temperatures are day by day it's pushing up. So in order to meet that, a lot of developments happens. So we also look at the all the structural alloys, which is titanium and nickel based, and also we also look at high temperature aluminum alloys, which are also coming up to compete with the structural iron based alloys. Okay. In the interest of the general public, I just want to give a brief introduction on the microscopy. What are the typical information one can get from this electron microscopy? But before even getting into that, if you look at the basic physics of the electron beam interaction on the material, especially solid material I'm talking about, when the electron beam interacts with the solid, you get, there are two primary type of signals. One is forward scattered signals, another is backward scattered signals. The material thickness is very high. We get primarily the backward scattered signals, which forms the basis for the scanning electron microscopy. And then you get the information for using imaging, using secondary electron or backscattered electron. And then you get the diffraction information, that is electron backscattered diffraction, which also talks about orientation microscopy these days. And also you get a spectroscopic information using X-ray, energy dispersive analysis, and electron energy loss spectroscopy are also possible. And the most popular one recent times is electron channeling contrast imaging of defects even from the backscattered detector one can do. This is coming out to be very important information. And if the material is made thin enough for the electron to transmit, then you get the forward scattered signals, and that is where you can look for transmission electron microscopy techniques. And this is again a very powerful technique. You can get the very detailed information at a very localized region. And what you are seeing here is a bright field T micrograph of a cross section of a coating, and what you are seeing also is corresponding diffraction data. In addition to these, you can also obtain very specialized diffraction information from the very localized region using nanobeam electron diffraction, and also we can use convergent beam electron diffraction, which will give the information about the crystallographic or symmetric information. And in addition, we can also get a very detailed spectroscopic tools with which you can get the local chemistry similar to what I have just described in SEM. So this is very basic information about the electron microscopy and what we can get out of it. So now I'll just talk about what we have at IIT Madras. We have the Central Electron Microscopy facility, which we developed in the last 1 decade. And it houses quite range of microscopes from, the very basic microscopes, 120 kV to 300 kV microscope, and also field emission gun, SEMs, and lot of sample preparation units. And through this center, we also offer 2 interdisciplinary courses on transmission electron microscopy. Every year, across the departments, scholars take this course. In fact, it's a huge demand for these courses. And we train almost 20 research scholars every year who become later independent users of the TM. They not only enjoy using this microscope, they also help their colleagues and others. That's how the whole center demand is met, and quite a bit of demonstration has been done in this regard. So at a given point of time in any year, about around 40 research scholars will be engaged in this kind of research, and who are also helping in the other who require this techniques. So in order to take this center to the next level, the investigators propose this research proposal so that we can take this center to the next level of sophistication and instrumentation facility. So these are all the investigators. I will briefly introduce them. This is myself, and Dr. Subramani Sharma belongs to the Department of Metallurgical and Materials Engineering, and who engages in primarily microstructural mechanical properties correlations in engineering materials. And Professor Srikanth Vedandam is from Department of Engineering Design, who also engages in modeling. And then I will just give the brief about the details of the research highlights later. And Professor B.S. Murthy again belongs to MME. Currently, he is at IIT Hyderabad as a director who works on nanomaterials, who also championed the establishing the National Facility of Atomography, and which we have seen in the introduction slide, which is the first equipment remotely operable across the country. And Professor Sudhakar Chandran from physics, who works primarily on multifunctional and multiferroic materials, who is also part of Central Electron Microscopy core team which maintains that. Professor Harikumar, who belongs to MME department, who engages in the computational thermodynamics and who helps all the colleagues, to whomsoever interested in this Gibbs energy modeling of materials. Then Professor Somnath Bhattacharya, an electron microscopist, belongs to MME department, who engages in advanced transmission electron microscopy method development, simulation, and experiment. And finally, Professor Satyesh Kumar Yadav is also belongs to Department of MME, who engages in first principle thermodynamics and atomistic modeling of materials. And these are all international collaborators who are going to work along with us towards building this research proposal and the research center. And this slide shows the focus and objective of the proposed center. On the successful implementation of the center, as I just briefly mentioned, the center will focus on the energy 2D materials and nanomaterials and advanced structural alloys through the highly advanced characterization and modeling tools. And these are the our aim to add on to the existing facility, so that to enhance the capability of the microscopy tools. So that is one of the primary aim of this center. And if you look at the specific objectives of the center, and which is categorized under the 3 categories: engineering alloys. Primarily, the center will focus on the designing using the computational thermodynamic and kinetic modeling, and then process optimization, and looking at the microstructure property correlations in engineering knowledge. Similarly, in the functional materials also, we will standardize the synthesis parameters on a local atomic and electronic structure of max phase, and also we will try to establish the defect structure property correlations in the multifunctional materials. So these above experiments will be augmented by the modeling activity by the investigators, what I have just introduced. Now what I'll do is each of the investigators, what actually they contribute towards the goal of this proposal. The first one is Professor Harikumar's activity, who engages in CalFAT-based approach to alloy design, and he also helps us to arrive at a design by where we can tune the chemistry and stacking fault and phase fraction to the first principle, and he also helps to simulate the kinetic phase transformation, and finally, these results can be validated to the microscopy techniques. And this is slide shows the research activities of Professor Sharma, who works on the advanced high-strength steels, for example, which is shown here. You all know that all the automotive sector is day by day demanding the very high strength and lightweight, at the same time strength ductility combination and so on. So which clearly exhibited by this popular banana diagram. And what you can see is that though there are several grades of alloys established already, but there is a huge scope for the futuristic material. So in this region, the research is focused, and for such kind of achievement, the method which is being followed is through this like CalFAT, and which will give them an idea to optimize the high strength ductility and optimal stacking fault energy. So which is shown as in the case study here. For example, this particular graph shows what kind of the chemistry and will match the required stacking fault energy or tailored properties, right? So for such a alloy design, the material will be produced through an ingot metallurgy route, and then the microstructure evolution at each of this stage is quite important. So in order to study that microstructural evaluation, you can also do such an experiment at the laboratory scale with using the Global experiments. That's what is shown here, and then where you can establish the the process map where the safe region of the material metal working, and then corresponding microstructural evaluation can be studied nicely. And what you are showing here is the APT map, where you see that the segregation of carbon and manganese in the interfaces for a given steel. In this case, it is medium manganese steel. It is developed by Sharma's group, and this is the property. What you are seeing is quite interesting. You see that such a high strength and ductility combination, the material exhibits a heterogeneous flow, and which in turn the reason for such a flow is about the twinning. This is a transmission electron microscope image which shows that twins which forms and during the deformation. And this slide shows the again another type of advanced high strength steels from my group, and this is again a popular steel called punch and partition steel. The core idea here is keep the chemistry simple, least alloying elements, but then the partitioning of carbon in arsenate and stabilizing them in a two-phase microstructure will provide a range of strength and ductility combination like what I have just mentioned. So that is an idea. So we are still working on it. We have developed a couple of composition. We have patented it, and it's going on. So the other area which I am also concentrating is the grain boundary and interface properties of the complex engineering alloys. This is a microper alloy. What you are seeing is a grain boundary precipitation and phase transformation. What is shown here is kind of a spinodal decomposition we could see, and then also the segregation in the grain boundary at a very local level. See, such investigation was never possible before because of today we have the sophisticated tools to quantify them, and also we have thermodynamic tools to support what we experimentally find out. So that is one important aspect. And this slide shows Professor B.S. Murthy's activity. He engages on developing new high entropy alloys, and this is all atomic resolution APT maps, which shows the phase segregation and elemental segregation. And he also intend to study this kind of alloy through in situ microscopy as the center establishes this facility. And the next one is Professor Srikanth Vedantam's activity, who basically do the base field model for microstructure evolution, which primarily augments the our experimental research, especially on the grain boundary engineering. And he also now works on the base field model for abnormal grain growth, which is a long-standing problem, and which he nicely modeled by showing the thick boundaries or complexion transition in the boundaries, which is nicely shown here. So the next one is Professor Somnath Bhattacharya's research. So what you are seeing here is atomically resolved 3D structural reconstruction of small quantum dots in the indium nitride nanoparticle. What you are seeing is the tomogram, the single projection. So such a work has been done very first time. So the Nanoscale journal has put up his research in the cover page. That's quite interesting idea. And Professor Somnath also works on the determining the despacing in the nanoparticles and its effect of carbon films in the grids, right? How it affects the despacing in the nanoparticles. So he developed the method to correct them and then accurately measure them. So it is not that if you have a sophisticated equipment, you have a better characterization facility. You also need to develop methods so that in a way, Somnath's work is unique and it's very useful to the electron microscope community. And Somnath also works on characterization of nanomaterials at atomic scales. And this is about titanium alloy, where he has looked at some of the important phase transition, and he also works on max phases, and this is some of the results from the in situ heating at the very local level. So, and then I move on to Professor Sudhakar, who primarily focuses on works on multifunctional material, and he extensively uses the high resolution microscopy to arrive at defect structure property correlations. So all this spectroscopic and microscopic techniques he uses. And then one of the classic example here is the microstrain in the bismuth iron oxide, where he sees that pseudo cubic phase within the rhombohedrally distorted perovskite nanoparticles. You see, such a localized phase transformation is not possible. To study without this highly sophisticated techniques. Resolve in such a local region. And the other case study shows in the right hand side is the effect of defects, especially oxygen vacancies, on the optical, magnetic, and multifunctional properties. And Professor Sudhakar also works on the battery materials. What you are seeing here is manganese disulfide nano sheets, where you see that he characterizes the defect rich region and the defect suppressed region, and then how it relates with the electrochemical properties, and which is being used in the lithium-ion batteries. And finally, this is a work of Professor Satish Yadav, who does the atomistic modeling using density functional theory. And a classical example here is shown is the metal ceramic interfaces are assumed to be atomically sharp, but using the atomistic tools, he has shown that the chemically graded interfaces between these two materials are thermodynamically more stable than the sharp interface. The another important aspect of Professor Satyesh's research is that what you are seeing is some of the simulated interface of germanium gadolinium oxide, and this is a simulated STEM image. So the interesting point is, even though you have the simulated STEM image or microscopic image, what is the the interface terminating phase is very difficult to identify, whether it is germanium or oxide or oxygen. So such an experiment, such a atomistic modeling clearly reveals that in this case, at least, it is an oxygen which is terminating phase. So what is I'm trying to say is, though you have very high resolution microscopic techniques, you need this atomistic modeling to augment the cells and then proceed further. So that is very important. So that's all from our research highlights, which is going on currently. And what I would like to say finally is the Center for the Advanced Microscopy and Materials will develop futuristic materials from application point of view using the state-of-the-art advanced characterization modeling tools. And I would like to request all the interested and prospective scholars to, if they want to interact with us, to kindly look at this website and reach out us to whatever you want to do, whether you want to join us any project or a PhD program, etc. That's all from my side. Thank you for your attention. Over to Gerhard.
Well, thank you very much, Shankar, and also thank you very much for this very informative, very nice presentation. I think it covered a lot of ground, and I could imagine that there are a lot of questions. I already saw some in the audience, but I would like maybe to start this discussion section by asking some questions from my side, and then maybe later we will return to the questions from the audience. You have nicely shown the capabilities in your center for doing something which nowadays I think is regarded as very important, which is correlative microscopy, to basically analyze material with TEM methods, which are very dedicated, as you have shown. You can really look at the atomic column itself and what it basically does, even under stimulus. Then you, on the other side, have atom probe tomography to look at position of each atom, give or take a few percent, which you don't catch in the detector. This is, I think, very important and impressive. But what are your views on in situ methods? Because I think this is really answering, or could answer, many questions of in operando materials behavior. I think it will be the next big thing, and we know for many years these methods based on changing the temperature or changing the strain state, but nowadays there is much more possible. So what do you envision also in terms of your center, what you want to do?
Exactly. Thank you, Gerhard, for that question. We have just started looking at the in situ techniques. In fact, we have not established yet. We have just bought a few holders, just beginning that exercise. But and in the SEM level also, Sharma has taken some steps to look at the institution. I think already he has established something. Probably Sharma can also answer the question partly.
Yeah, Gerhard, good evening. So basically we are having in situ heating stage both in the TEM and SEM. So that gives us an ability to understand materials and for example, the interface mobilities and interface segregation and as a function of temperature and time and so on. So yes, as I said, as you said, it is very important that, but one of the things is that the environment inside the microscope is vacuum. So whatever we do in that may not be representative of what is done in other atmospheres. Unfortunately, you cannot do these things in other atmospheres. So So there is always that question. For example, the grain growth, which we are observing in vacuum, is quite different when we do it in air. The same material under identical conditions. So these are some things. So we may take some information out of it, but probably it is not relevant to the practical, and it may not be directly correlated to practical. So these are some of the observations. But as you said, it is very important that we, correlate.
On the SEM level, you could think of environmental facilities, right?
But still, it is still not.
It's still not the same atmosphere.
Not the same as the ambient pressure, right? So
yeah. I was also wondering, you have some directions on functional materials, and so you could also think of, for example,
maybe I can comment on that. So what we are planning to do is, I can give that lithium-ion battery as one example. There are special holders where you can assemble the battery, very tiny battery, where the electron beam is still transparent, and you can look at the interface between the cathode, anode, and then the electrolyte, solid electrolytes, what exactly happens, and therefore how the batteries can be improved in terms of their performance. So these atomistic level reactions is something one has to get, and there are many labs worldwide. They are starting, but it's a very challenging experiment to do. So that's something in our Pronto experiments we would like to take up, of course, develop the techniques and bring the facilities that we can do here. Yeah, that's something in the pipeline in the center's interest.
Thank you very much. I think that's very important. I think it's very challenging, but I think it also could lift this type of research really to top world level, because it's something everybody wants to know, right? I mean, how in operando does the interface react between electrolyte and electrode, for example? So if you can answer this, that would be great. Another question which I have is, you nicely showed already you have computational capabilities, so you do simulations, and on the one hand, and you do the atomic scale investigation in real life on the other hand. I think that's also very good, and I think it's almost necessary in order to understand some of the very complex things we see today. But how is the planning about doing virtual transmission electron microscopy? So do the full loop in terms of taking the simulated structures as well as maybe during operation, and analyze how the full TEM analysis would result in image formation, and then compare these with the real life experiment?
Yeah, that's a very good question, Gerhard. Yes, Dr. Somnath is completely doing what exactly you're asking. May I ask Somnath to respond?
I think he's not here.
He's not here, is it?
Maybe Satyesh can answer.
Satyesh?
That's right. So this is the exact same thing which actually Shankaran was showing in one of the slides, and I was part of the publication with Professor Somnath. So what we did is he came up with really fantastic technique to remove the amorphous layer which got deposited at the interface between gadolinium oxide and GE. And even then, it was not clear whether GD203 was terminating in oxygen or it is terminating in germanium. So I did this atomistics DFT-based simulation with both oxygen termination and gadolinium termination. I gave that to Somnath. So Somnath simulated it. He simulated a micrograph and then compared that micrograph to the actual micrograph he obtained from TEM. And that's how we figured out that it is probably, it looks closer to oxygen termination compared to gadolinium termination.
Very good.
That's what we are working towards.
Mm-hmm. And do you also plan to integrate, for example, artificial intelligence, machine learning algorithms into, for example, motif extraction or so, if you think of functional amorphous oxides and things like that?
Yeah. So there are plans of integrate. So especially within density functional theory, it becomes really difficult to handle systems which are more than 500 atoms at the max. So that's where the next plan is, that let's increase that capability, even though not compromising on the accuracy which we get from DFT, and getting to more realistic system which a micrograph can easily capture.
Mm-hmm. Very good. Then maybe last question for now from my side is, I think worldwide it's clear that we need to go much further in terms of green energy. And I think in terms of climate, India has, compared to Germany, a distinct advantage of having more sun hours. So photovoltaics could be really a big issue. I think I saw it on one of the slides, but not having the impression that this is like a major part. So do you plan to also do investigations in this area? And then I have the feeling that most of these materials are really beam sensitive. So when one does TEM, one always has to worry about introducing defects by analyzing the material. So have you thought also about this aspect?
Yeah, very good. Sudhakar, you can answer this.
Yeah, so I will take up this question. So we in our group, we also work on photovoltaic material. As you rightly pointed out, the recent generation solar cells basically are beam sensitive, like perovskite, for example.
Absolutely.
So it's very challenging to even put them under the beam and then study. Understanding the defect structure and its influence on the photovoltaic property itself is a big challenging topic. And I see very recently, the work highlighting what is the role, whether is it augmenting the property or it's killing the property. So it's very challenging. So we are planning to do these things, but beam sensitive samples we can't do much. But there are versions of perovskites which are very stable. Generally, if they are stable at high temperatures in external conditions, as we heat treat them, they generally tend to be stable in the electron beam conditions. So like double perovskites, which are the stable materials for solar cells, which we are developing, both from the fundamental understanding point of view, as well as from the point of view of understanding the defect structure, how it influences the photovoltaics. So I believe these materials will be very apt for the electron microscopy studies. Yeah.
Yeah. Do you also plan on having fast cameras and maybe some like single electron detectors? Because this would be the next step in order to do very short time experiments, minimize exposure, and getting much more into the direction of beam
damage. Yeah. So any beam damage or beam influence changes in the materials itself is something very interesting to know. That requires a very quick response cameras, and also of course it should not damage the field emission gun itself. So we have a lot of plans on that. Long way to go. Certainly. Yes.
I think it's just good to make maybe some people who distribute the money available, they should notice that this is not the end of the development. You are at a very good stage, I think, in developing the center, but there is so much more one can do with always having the best equipment, and there is a constant development, and I think one should make people aware that if devices are more extended, capabilities are extended, and this might be important for the future.
The direct electron detection that has recently come up, right?
Yeah.
So they call it as DED. So has it come in the TEMs as well?
Well, as a prototype.
EBSD cameras nowadays.
Yeah, prototype. I think Jülich is going to get one or having installed one already, and I think in a year or two you can buy them if you have the money available.
Yeah, of course. It's expensive. Yes.
Yeah.
Also very sensitive, so you have to be very careful.
Yeah, and really low dose. I mean, you can really go to the lowest dose possible, because going beyond one electron is not possible. Right?
Yeah.
Well, thank you very much. I think I would now try to go to the questions from the audience, and maybe try to select first the ones which I regard as being of interest to the larger crowd. And there was one which was asking, how do you cope with the microscopy challenges in materials with heterogeneous microstructures? for example, bimodal grained materials. So I think it's addressing the complexity, and one always needs to keep in mind, maybe also to the general audience, that what one does in transmission electron microscopy is to look at the projection of the interaction of an electron beam with a lot of materials, a lot of atoms. So that poses some very important questions, and I'm sure, for example, Shankaran or anybody from the group can answer this question very nicely.
Yes, thanks, Gerhard, for the question. Yeah, you are right. And what I'm not clear about this question is he talking about atomic resolution or is he general challenges?
I don't know, because I just see the written question, but I would say maybe not atomic resolution, but maybe more looking at microstructure size or feature size. So.
Yeah, so this is yeah, really a challenge, and then we have been now developing some techniques to measure the particle size, right? Like if you talk about bimodal distribution, there are some special techniques. You cannot just, for example, the way in which you count the particle in an SEM or an optical image, you cannot do it in the TEM. There are special procedures which takes care of the projection. What is the projection, shadow projection, correction, and then you do the quantification. That's what currently we are doing. And yeah, and the other challenge is you cannot just go to very low mag and then take, and or very high mag to take. We need to reach an optimal magnification to get the quantitative data. That remains as a challenge. Yes, I agree. Mm-hmm. And Sudhakar, you have any other experience in this? You can share. Yes.
Yeah, I can comment on the heterogeneous microstructure, not on the bimodal grained material, but heterogeneous materials are always very challenging. For example, one of the great challenge, the multi-layered materials that are used in very many applications. For example, the simplest one is the magnetic tunnel junctions, which has at least three different layers. So looking at the interface between the layers, if you want to do that in microscopy, first of all, you have to make them thin enough so that the electron beam can pass through. So the cross-sectioning of the such a heterostructure itself is a big challenge. So, and also in nanomaterials where core shell structures are made, the core being one kind and shell being another kind of material. So it'll always be very challenging to characterize these material. We have a lot of examples in our own group where we studied about the cadmium selenide being coated with zinc sulfide or zinc selenide, and how difficult it is to. I mean, of course, we were trying to look for how these two different materials interdiffuse across the interface. It's very challenging to do this, especially if you want to get the chemical information as well.
Mm.
Yeah.
Thank you.
Yeah, I think the thickness of the materials is very crucial, because you can't compare with theoretically developed images, they're high resolution images, because these quantum dots, even though they are few nanometers, is much thicker for theoretical simulations. Yeah.
Yeah, so one point to add, in order to just check the thickness, conventionally the convergent beam electron beam diffraction is used to calculate the volume of the material. If you are interested in quantifying the microstructure quantities, and if you have an electron energy loss spectrometer, then very instantaneously we can also record the local volume. That is another advantage.
Thank you very much. Then there's another question which reads, how long does microscopy development take? I interpreted this question that it's basically a general question, like how long does it take to reach a result, which might be important for all the people in the audience who might work in application or industry, where maybe time is money and counts more than in academia. No, it's difficult to answer in general, but maybe some words can be said on like your typical experience.
Yeah, I mean, in our case, it all depends upon what kind of sophisticated you go for. Basically, if you are looking for a very basic mission, then there will not be much time will be spent on creating the appropriate environment and operate the microscope. But the moment you are interested in sophistication, for example, aberration correction and etc., and taking care of the environment is a huge challenge. In fact, IIT Madras has a huge experience in this. And of course, Gerard also has huge experience in creating environment and so on. So the answer lies exactly what type of microscope you want to install.
Mm-hmm. And also most important thing is the sample preparation. The sample preparation itself is a big challenging. I mean, since it's for general audience, I would like to say here, people come with a big chunk of piece and then say, I would like to run the TEM. It's not possible. Even if it's a micron size material, the beam is not transparent. So, and sectioning it and making it transparent enough is something, I always tell my students, it's the kind of art everybody should learn. Just operating the microscope is not enough, but you should also know how to prepare the materials so that, you can get the right information. Of course, not modifying the material itself in the process. Yeah. So though nanomaterials are the ones that go right away onto the grades, but it has its own challenges in terms of interpreting and getting the information. Yeah.
I would also like to add here, it's really important to distinguish between going to the atomic level and trying to do high resolution where you see atomic columns, or whether you want to investigate like the microstructure, what's the grain size and grain size distribution. Even that can be very challenging, and even that can be very challenging also in scanning electron microscopy images, because the interaction mode and image formation is different, and you have to know how to interpret it. So if you already know everything and you just take the image, it's a question of hours. But going and getting to this point is a question of years. So the answer, I think, lies somewhere in between. Next question is, can electron microscopy also be used for medical purpose? So medical materials, I would probably guess.
Obviously, yes. Sure. A lot of biological materials are being used, investigated using electron microscopy. In IIT Madras, we don't have such. We have very, very basic facilities. And for example, preparing the sample is a challenge in the biological material, which requires very special tools. Probably, the medical schools always, they engage electron microscopy extensively. Molecular biology department definitely uses a cryo-TEM. Yes, that is there. That is the primary requirement. Even in a normal microscopy, you need a cryo holder to investigate these kind of materials. Right now, we don't have, IIT Madras don't have, but other institutes, which is basically biological sciences, they have all this.
Thank you. Maybe I answer directly a question. No, it's not possible to put live matter, so animals or any type, into the microscope. We already addressed the issue in TEM. It's a vacuum environment. So that unfortunately is not possible. Also, the biological investigations, medical investigations, as Shankaran just explained, use cryo-TEM, so you deep freeze the material which you investigate, and that would also be difficult to survive. Also, in terms of introducing the matter into the TEM, whether liquid, gaseous, or solid, I would directly answer it could be liquid. It's mostly solid, and it's not gaseous, because there is nothing to be seen on a gaseous material in terms of electron contrast. There was one question: what type of software codes and modeling tools are being used for simulations?
Maybe Satyesh?
Yes. So at atomistic scale, we are using a basic theory called density functional theory to calculate most of the materials property. Along with that, there are other potentials that are available. Use that as well. DFT is implemented in something called Vienna ab initio simulation package. That's what we use, but there are many other. This is commercial. There are many other free if someone wants to try out. LAMPS is another freely available software to model atomic materials at atomic level. That uses empirical potentials. Professor Hari Kumar is with us. He can also tell more on how to get thermodynamics data with CalFAD approaches.
Yeah. Professor Kumar, if you like.
Yeah, I am here.
Good.
Hello.
Hello. Good to hear you.
Yeah, hello, Gerard. So I work with computational thermodynamics. So this is nothing to do with microscopy directly, but the design of materials usually start with some theoretical estimation of the expected microstructure. So for that, it is necessary first to do some calculations that leads to a certain microstructure, so that you know what composition domain to investigate. So once the material is prepared, then the microscopists, of course, and other people who want to investigate the material come into picture. So in general, designing a new material doesn't start with straight away doing the experiments. We start with a set of computations where you can narrow down your search region. So this is where the computational thermodynamics and kinetics and all those things come into play. And computing the microstructure, you have also some techniques, but that is nothing to do with microstructure, but nothing to do with the electron microscopic type of images, but microstructure at a gross level. So in that sense, you have a method called phase field modeling, which also is a technique to generate the microstructures using computational techniques. But this is not like the microstructure you see under an optical microscope in that level. So it's a mesoscale type of a simulation.
Mm.
So these are the software tools that we have. We have all kinds of computational tools for thermodynamics and kinetics. Then, of course, this DFT also we use in the context of CalFAD as an input to generate better energy functions. Yeah. Okay, so I suppose I could answer like this.
Thank you very much. I also think that it was already explained that you also have the tools for going from the simulated structure to basically the simulated TM image, which could then be compared. So I guess, and I would have expected that at IIT Madras, the full loop is available, which I think is very important, and it's very good to have. This also answers one question that one, of course, can use electron microscopy also to study civil engineering materials or building materials. They are solid, they are either crystalline or amorphous, and thus they can be studied. And I think not only by electron microscopy, but by the combination which is offered in this center, this can really give you a strong push forward in your research on these materials. So maybe I go now to some more specific questions, which I have seen. One was in between. Interesting question. Will carbon nanotubes be affordable as building materials someday? That's a good question for you as a group. So I'm interested to hear the answer.
Yeah. Maybe I can just address a little bit, but of course we, for example, I don't work on the carbon nanotubes, but there are colleagues in physics department, they work on carbon materials. So carbon nanotubes, yes, at least I see nowadays in Bangalore, a company coming up producing carbon nanotube inks and solutions in large batches. So I think it's becoming more affordable. But then the question is, if it depends on what kind of carbon nanotubes you want. If you say I want only single wall nanotubes, then it's going to be very costly. And but if you don't care about whether single wall, multi wall, then it's cheaper. So I think that's where the state is, but still the processes to get the carbon nanotubes in large volumes is always challenging. And so it's more a question to the chemistry and other people who are developing the carbon nanotubes in large scale. Yeah.
I completely agree. I think in terms of having a bundle of quite different ones, it's today actually a material which is produced, which you can buy, and it's even not so expensive. But if you want to have a carbon nanotube of a certain type and then maybe several kilometers long, this might be still a challenge and not so much affordable. I completely agree. Then there was another question which goes now to the to your presentation, pointing to slide 11, if I remember it correctly.
Gerhard, I saw that. I have answered it to him.
Okay.
It was regarding the serrations in the flow in the stress strain curve. So he was asking whether it is because of twins or is it also due to the dislocation solute interactions. So dislocation solute interactions are not easy to image. So yeah, possibly they are also contributing to the serrations. Yeah.
Okay.
So it's a contribution of that is well known, right? The quadral atmosphere is not is generally responsible for the serrations in the dynamic strain aging or strain aging. So we can't prove it directly, but then it is assumed that these things can contribute. Yeah, but twins also do contribute to the serrations. These are also well established. So possibly both of them are operating in that regime.
Very good. Thank you. Then I have one. Does nanomaterials, nanobots used for modern surgeries are designed through electron microscopy level designing? Or could rephrase the question and say, is this within the scope of the center to look at those things also?
They are nano. They are definitely nano, but one doesn't use nanometry in a microscopy to design it. One only one looks at it in the microscope. You don't design it, is it?
Yes.
Nano because it has to enter the body and it has to do the surgery. So, I mean, functional. But I don't think anybody in our group is working in this direction.
Yeah. So primarily the energy and transport materials is the focus.
Then I have here one question which I just read because I don't really know what the question is, but it might be still interesting. If we will use green natural energy for that, I don't know what that refers to, it might be helpful for these atomic structures. So I guess the question means, how can electron microscopy help using or developing materials for harvesting green energy? This at least is how I interpret the question.
Yeah, so that's a nice question. Of course, for example, in solar cell, always people would like to use, for example, one specific solar cell I will point out, which is like dye-sensitive solar cell, where the dye itself is an organic component, but people would like to use a natural dye, which is available in some fruits and plant pigments. So of course, if there is a dye which we find which is going to be useful for solar cell fabrication and which can last longer in terms of its operation, that'll be great. But as far as when it comes from the atomic structure point of view, I don't know whether TM will be helping in any way to find such material. Because most of these dyes, even the organic dyes, and they don't sustain in the under electron beam.
But if you think about perovskite and maybe tandem solar cells, where interfaces are so important in terms of preventing the recombination before they reach the electrodes and so on, there might really be some chances. Again, I think problem there is beam damage or beam sensitivity of most of these materials. But I've seen some examples where people have found a workaround. I think this is really work in progress, right? I mean, we are currently at the edge. Many things we cannot yet do because the methods are not yet there or they are too expensive. But I think once they are developed, and I mean, this takes maybe a few more years, I would say, really some much better answers could be developed from this type of research to really go to the next level and make better materials. At least that's the hope.
Yeah, sure.
Then can electrically conducting polymers be used in STEM? Used, I interpret, as being analyzed.
Yes, we have we have produced some polymeric material results people are using. That's possible, yes.
Mm-hmm. What kind of electromagnetic lenses are used in advanced microscopes?
Oh, I think probably we should recommend him to go through our NPTEL lectures.
I think maybe one could say, without going into the detail, that these new correctors, which are typically hexapoles, really have made a quantum leap in terms of being able to interpret the intensity which you obtain on the flat screen below the specimen, and which results from a very complex interaction in 3D when the electron beam goes through the specimen. Because in previous lenses and even in textbooks, you read that aberrations in electromagnetic lenses are unavoidable. It is true, but you can correct them with these correctors, these hexapoles nowadays. And that means that you can really get an intensity distribution which allows you to go back to analyze the positions of atomic columns in space. Before, you could only do complex image simulations and then compare the results. Nowadays, you are very close to what you see is what you get. Anything else maybe requires, as Shankaran says, a separate lecture. Now, the last one which I see here is how metamaterials are prepared.
Okay. So what I understand is metamaterials prepared for the TEM examinations, what I'm assuming. So,
I guess.
So basically, yeah. So we have to mechanically thin down to few nanometer thickness, typically around 50 to 60 nanometer thickness foil, and then you have to in a conventional manner, you have to punch out 3 mm disc and then put it in the holder for jet polishing. Further, it is polished by electrochemical methods, and then it is made electron transparent. But in modern terms, if you want to look at it, people directly use focused ion beam to prepare samples. So depending upon what kind of facilities you have, and use it, but still primarily most of the people use is mechanical thinning and just punching the 3 mm disc out of the foil. So that's the way.
Mm-hmm. Yeah, thank you. Now there are some questions which are still left in this chat box, which we have basically addressed already. So I don't know if we should really readdress them again. So what's the general opinion on your side?
Yeah, I think if it is, yeah, we will most of the questions are answered, I suppose.
Yeah.
Maybe Richu can comment on that. Probably she is.
If most of the questions are answered, then we can wind up, sir.
Okay.
Yeah.
Because you have another seminar lined up at 6, right? Is that?
Yeah, that's just starting.
Yeah.
Okay.
So
I think the questions are basically answered, and some of them are just different wording of a question already asked and already answered. So I think
yeah, sure. Yeah, all right. Thanks a lot, Professor Gerard, for being with us today and taking all the time off and being with us and answering all of the questions. It was wonderful to have you. And thanks a lot, Professor Sankar, and everybody on the panel. We're very happy that you could spend all this time and talk to us about the research and answer the questions from the audience. And we wish you all the very best. Thank you. Thanks a lot.
Thank you for all the coordination and fantastic arrangements. Yeah, thank you.
Thank you.
It
was my pleasure. Good to see all of you. Bye-bye.
Schönes Wochenende.
Danke gleichfalls. Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you, Sudhakar.
Yeah, thanks. See you. Bye.
Thank you, Satyesh. Thank you, Sharma.